All right, so for today's problem, I would like you to write me a function called isGraph bipartite. Okay. So do you know what a bipartite graph is?
I don't. Do you mind repeating it for me?
Yes, I would. Yeah, I would love to tell you what a graph is. So a graph is bipartite if the nodes can be partitioned into two independent sets A and B, such that every edge in the graph connects a node from set A to a node in set B. And this is an undirected graph.
Okay. Okay. Um, okay. And the function is to detect if a graph is bipartite.
Correct. You are to return true if and only if the graph that is the input is bipartite.
Okay. Sounds good. Okay. Return true if the graph, if and only if graph is bipartite.
Correct.
Return false if it isn't. Do you mind telling me what the input of my function I can expect to be?
Yeah, so you're gonna get so you can decide if you prefer an adjacency matrix or adjacency list. But
Okay,
whatever you
I will-
prefer, that's fine. But you gotta let me know which one it is.
I will take an adjacency matrix then.
Okay.
I think. Uh, just on initial. Maybe I'll switch to a list later.
Yeah, we could switch later, but you gotta explain why either way. But that's fine.
Okay. Okay, I'm picking an adjacency matrix because we want to check if every edge connects A to B. I want to use a matrix for now because I want to be able to look up edges pretty quickly. So I'm just picking the matrix. Now I need to think about how I can tell if every edge connects to A and B, given this adjacency matrix. So the two independent sets are arbitrary. I guess I can define what the sets A and B are. So,
Yeah.
okay. I guess I'll start by just making an example. Let's call our nodes A, B, C. Then it's 2D list, so I will draw my columns. Oh, actually, I'm gonna switch to drawing. Do you mind if I?
Yeah, I'm following you.
Am I allowed to do that?
Yeah, I'm
All right.
following you.
All right. So I'm gonna have A, B, C, A, B, C. Adjacency matrix. I think it returns true for the own nodes. I'm just gonna put ones and zeros. So 1 is true.
All right.
Then we have connections. So let's say A and B is not connected. B and C, I guess, is connected. And A and C is connected. Okay. And so I can arbitrarily create a set. So let's say AB is one set and then C is the other set. Return true. Oh, I don't get to decide whether two nodes are connected, right? So the adjacency matrix will just have that in there. Okay. So now I have to find these two sets. So brute force would basically just be iterate through every possible, I guess, division of the two subsets, and you just check the adjacency matrix for every node in blue, check every node in red, and see if the item in the adjacency matrix is 1.
Sorry, was it a question?
No, I'm just thinking
okay.
to myself.
Sorry.
Every edge connects A to B, and just to confirm, a graph is bipartite if every edge has to be connected from A to B. So that means that if a node in set A connects to another node in set B, set A, that would not be bipartite. Is that correct?
Correct, but I want to be a bit more precise in that. So what you said is true, but I'm not sure if you got the key there, which is that it's for any set. It's like if there exists a set A and B. So it's not like you pick A and B. No. It's like there exists a way to divide the graph A and B, such that what you said is true. You don't get to pick A and B. I mean, you can pick it, but that's worthless. But so you don't get to pick the sets A and B, but there exists a set such that is true. Does that make more sense?
Yes. Okay. So, yeah. So I guess then the intuition there is somehow as you're you check. I guess okay. Let's remove the A and B sets. So you takes node A and then you take node B, or you'd compare every two nodes and you just say like, are these two connected? If they are connected, they must be in a different set. And through that way, you're trying to go through all of the node combinations and see if there's any contradiction that creates an impossible result. And if there's an impossible result, you'd return false. The problem is, does that work, I guess, is what I'm thinking. So for now, I guess my initial idea is loop through every node combination of A and B. Node A, node B. If connected, check that. If connected, A must be in set 1 and B must be in set 2. If they're connected, we need to make a check then that sees if the nodes are like already placed in a set. So check if A and B are already placed. And then we have like cases. If both of them are placed, we can like confirm true or false. Both are in sets. If they're connected and they're both, okay, if both of them are in the same set, we can return false. Return false. If they're in different sets, we can continue because that means this connection is fine.
Okay.
And then we have the cases where like only one is in a set and the other isn't, which means that the other one would have to be in the other set. Set other can be in different sets. Okay, so those are the cases. Well, actually, there's one more, which is if both of them are not in a set. And I guess this. I guess it doesn't
hold on,
really.
no, I just want to clarify. Well, what do you mean by if both are not in a set?
Like, at the beginning, we haven't partitioned any nodes into like sets A and B.
Okay, I see.
So
yes.
Yeah. I
So,
guess
yeah,
in the
that
first
makes-
case,
okay.
we would just arbitrarily add one to one set because it doesn't really matter. So we just like put A in first set and then B in the other set, and then you can move on.
Okay.
So here's my thing right now. If connected, so we loop through every node combination in the adjacency matrix. If they're connected, we check, then we check the cases. So if both of them are in the same set, you return false. That looks fine. If both of them are in a different set, that's good. That's expected for bipartite. If one in set, other one has to be in different set, not can. So if one of them is in a set already, you just put the other one in the opposite set. If both not in set, then you just arbitrarily assign one to each. Okay. Now I'm thinking about, with an adjacency matrix, I guess the nodes would just be represented by index, which works fine with me, because then I can just put them into a set. I can just put the index into a set and not worry about like any incompatibility there. Is there a different way you would want me to represent a node, or do you think indexes are right?
No, indexes are fine. That's how they. If you want a matrix, then that's the only way they'll really be provided.
All right. So yeah, we can use index and then place in sets. Okay. And then yeah, if we loop through every combination, we can return true. Through every combination, that means we've checked like every node pair, and if none of them have created a contradiction of both of them being in the same set, then we're fine. So if loop through every combination, we can just return true, and that looks like the function. For now, I think, is there any edge cases that I need to be wary of? I've considered all the cases for when A and B are connected. If they're not connected, I just don't care, right? So if they're not connected, I just continue with the loop. Move to next pair. All right, we loop through every combination, so there's no issues there. If I have an adjacency matrix with no nodes, what's a quick question for you?
Yeah.
What's the expected result if the graph has no elements in it?
then it is considered bipartite because the rule is not violated.
Okay. So yeah, I guess that works fine with my function because if there's no node combinations, it just defaults to returning true, which is good. All right, then I think this function looks good to me. Do you have any comments about like what I've written, or if you want any more clarifications? Or
No, I think it's.
if
I think
not,
it's.
I'll continue.
Yeah, I think it's very clear. I will say though, at this point, do you want to consider do you want to consider evaluating what input type you prefer?
Input type I prefer. So adjacency list. I'm not too familiar with what it provides again. I'm pretty sure it's a list of connections. Like, I'll write it as a list of like two nodes A, B, and then it just creates a list of lists of the two things for all of the edges represented in the graph. Can you tell me if like that's the correct representation, or do I just assume that this is how an adjacency list is presented?
So in this case, we would have. So like in this case, A's connections would be over here. So A is connected to A and A is connected to B, right? So
Yeah.
so in this case, this is the essentially the edges connected to the first element. These are the edges connected to the second element, or nodes connected to the second element, etc. So in this case,
I
A
see.
would be considered to A and B. B would be connected to B and C, and C would have no connections, which is
I
not
see.
valid for
Not
our
valid.
undirected graph. But yes, that is.
Yeah, so this would be B and C. This would be required.
And DB would be on A as well, right? Because you have A, B over
Yes.
here. So A would be in this list.
A would
But
be
yeah.
on this list.
Yeah.
Okay. Okay, so if I wanted to look through, the main thing here is we have to loop through every node combination. The list makes it pretty easy as well because you know that you can go through every list in this like 2D array, and for each list it only contains the connections, which means because like here we have a line, in my algorithm I have a line where if it's not connected we like move through, so we just waste a cycle. But here in the adjacency list, we don't like waste any cycles with non-connections that we don't care about. So if A and B are connected, then you'd place them in different sets. I guess in this case, can I assume that like adjacency list would also have like indexes, or?
I mean, it's a list, so yes, list. I mean, sorry, do you mean, like by index, do you mean you can index a list? Because yes, you can, if that's what you're asking.
I guess, yeah, like what elements would be in this like list of connections? Is it just like anything that represents
numbers, so
A?
like indexes. So this
Okay.
so this, if you have your more literal, yeah, that'd be 0 and 1,
0,
right?
1.
This would
Okay.
be 0, 1, 2,
Yeah.
and this would be like 1, 2, I think, right?
Yeah, okay. So we skip through all of the like wasted cycles of non-connected. We have everything connected. It provides basically the same thing as the adjacency matrix. Does the code work still? Yes. Is it easier to loop through? I guess so. Loop through every node combination. So it can loop through every combination. It only shows you connected. So yeah, I guess in this case, I would say adjacency list is probably better for this function.
Okay, we can do that.
Okay, I'll just change this, yeah, because implementation's not there, so I'll just start with a list. Okay, then I'll start implementing the function underneath my comments. No, actually through my comments. So start with like A is equal to set and B is equal to set. So we have our two sets and B. We need to loop through every node combination. So I guess for let's call it index and connections. Enumerate adjacency list. So we're going to loop through every node combination. If they're connected, oh, yes. We don't need to care about non-connected, so everything is connected. I misspelled the numerator.
Sorry, can you just say
For
that again?
index.
Sorry, do you say everything's connected?
In the adjacency list, the only things
yes.
that are contained are connections, right?
Yes,
so
yes,
we don't
okay.
care about
Yeah.
non-connections. So everything's connected, so we have to go through each connection. Connection. So when we go through a node, it will either already be placed in a set or it won't be in a set. I'm wondering if it's better to just check if it's already in a set here. But for now, I'll just write that as a comment, and we can revisit it later as I implement this algorithm. So for connection in connections, so, and then we have, okay, so A would be index and B would be the connection. So I want to call this the second node, I guess. And let's call this first node. Right, so we have our first node represented by an index, second node is also an index, and then we want to check, in this case we need to check if first node equals second node as well. We need to check it in both. So if first node equals the second node, we just ignore it and continue. Then since they're different nodes, now we actually care about the connection. So if they're both in the same set, we return false. All right. If first node is set in and second, I'll do a large Boolean expression here. And this is in B. All right, so I check if first node and second node are in A, or if the first node and second node are in B. If they are, we return false, and the loop automatically ends. If they're not, if they're in a different set, that's fine, okay? Yeah, whatever. I'm just gonna copy paste this because it's a giant expression. First node in B, second node in B. First node in B, second node in A. Okay, so if they're in a different set, we can just continue. If one, okay, if only one of them is in here, if only one of them is assigned to a set, we'd automatically assign it to the other set. If I considered all the cases where, so the first two if statements consider all of the cases where both of them are in a set. I hope. First node in A, node in
okay.
B. Okay, I'm hoping the first two if statements have considered all the cases where both nodes are assigned to a set. So I'm going to, for now, I'll put it in. I'll check that later, but not too confident about that one. So we can assume that one of the nodes are not in the set now, in this elif block. So if first node in A, or I think I might restructure the if statements. I don't see a good way of writing this else if in like a nice way.
Okay.
Yeah, okay. Alright, let's just consider the first node for now. It can either be A, B, or none. And the second node can also be A, B, or none. That's the annoying part. I'm like the first if statement is too specific, so I think I'm just gonna use nested if statements at this point. If first node in A, if first node in B. If not, that means the second node must be in one. So I guess this is the else clause. Right? So if the first node is in A, the second node in A, then that's fine. If they're in the same set, return false. If second node in B, continue, else second node has to go into B, so B dot add what? B dot add second node. Okay, and then I just like copy paste this 3 times. If first node is in B now, if the second node is in A, if second node is in B, return false. If second node is in A, continue. And otherwise, add B to the first set. A dot add. Else first node must not be in a set. So if second node is in A, That means first node has to be in B. If second node in B, first node has to be in A. Otherwise, if both of them are null, I guess, oh, yes, this is the arbitrarily assigned one to each. So A dot add second node, sure, and B dot add first node, whatever. Okay, so that's the if statements taken care of. Does it cover every case? Yes, I'm pretty sure it does. What happened to my comment? Oh, there we go. Okay, I'm just going to move the comments to the top. This comment at the front, check if and set first. Well, I think at this point in my function, I've already like kind of chosen to go forward with the if statements, so I'll keep that. Okay, so I have like the core base of my logic, I think. I have the for loop. I check each of the cases where each thing is in a combination. And then I have the return true at the end once you finish looping through every combination. Let's just check all the if statements are considered. If first node equals second node, yeah, so if they're both pointing at the same node, you don't care. First node can be A, B, or none. Second node can be A, B, or none. That's 9 combinations. I have 9 nested if statements. Okay, I think that's mostly it for the function. Let's see if there's any edge cases that I can spot. If my list is empty, I create the 2 sets, enumerate does nothing, so I just return true. Is there any other edge case? I don't really see one. I guess if like, no, if the nodes are only connected to themselves, you just skip every for loop. Okay, I think that, yeah, that should be it for my function.
Okay. Sounds good. In the interest of moving us along, I want to know about the time and space complexity of this, please.
Yes, okay. Let's assume that there are 9 n nodes in the graph. Then that means we loop through every connection. In worst case, every node is connected, which means that you'd have to iterate n squared times in the first loop. All of the if statements, all of that, like set, adding to set, if statements, all of that is O of 1, which means that you just have these 2 nested for blocks that are O of n squared, which means overall time complexity should be O of n squared. Space complexity, we create 2 sets. Worst case, you assign all of the nodes to either set A or B, which means there shouldn't be any duplicate nodes, which means space complexity should be O of n in total.
Okay. Does the density of the graph matter?
How many connections there are? But in the worst case, the density of the graph is O of n squared.
Yes.
So I guess the density of the graph like matters, but it's already accounted in the O of n time complexity.
Okay. All right, sounds good.
Yeah.
Okay, sounds good. I want to move on to a second question now. This is unrelated to this one, so we can just scroll down past this and then just continue from there. All right. So this is a separate problem. For this problem, this is going to be about courses and prerequisites. Okay. So the goal of this problem is to write a function that can calculate a ordering. So you can call the function find order, and the input is going to be basically a set of courses or a list of courses, as well as their prerequisites. So for example, a prerequisite is a tuple consisting of 2 numbers. So courses are numbers, so like, you can think of them as indexes or whatnot. So let's say, for example, a tuple 1, 0 means that to take course 1, you need to take course 0 beforehand.
Okay.
So you can call them, yeah.
0 to take course 1.
Sorry, to take course 0, you can take 1 beforehand. I said it backwards. So
okay.
So the first number is a prerequisite for the second number.
Okay. To take course 0, we need to take course 1. Okay. And we need to find the order in which to take courses.
Yep, and then your goal is basically to find any ordering if there exists. There might not be an ordering, by the way.
Okay.
To find any order that is valid, to take all the courses in the list of courses.
Okay. So I'm assuming Boolean true or false true if there is any ordering that exists, false if there is no ordering that exists.
No, so you are to return the actual ordering, and if no ordering exists, you can return anything. It doesn't matter.
Okay. Can I choose the output like type?
Yeah.
Okay. I'm gonna choose list. Right. So to pick the ordering specifically, when would there not be an ordering? That's a question to myself. Sorry. Yeah. First thing I see is probably prereq loop. Like if you have 1 0 0 1, then you can't take course 0 or course 1, and then you're stuck. I'm gonna. Yeah, that seems to be the only thing. I'm assuming if a course has no prereqs, it's just free to take, right?
Yes, so, that's right. That's right.
Yeah, so the only thing you'd be concerned about is like a prereq loop where you have an impossibility. And then the concern here is how do you traverse whatever you've created to make an ordering. Okay, so you have courses and you have prereqs, and basically this forms like a directed graph of your courses are all nodes, and then prereqs are the edges. And then the question becomes, can you traverse the graph from start to end? I'm assuming the question requires us to take every course.
Yes, every course in the list of courses. So you're given a list of courses. In this case, I'm using the numbers as courses. So like course 0, course 1, for example.
Yes.
They will be. You have a list of courses, and you need to take all of them.
Okay, so yeah, can you traverse every node in this directed graph? If you can't, yeah, if there's a loop, you can't. Wait, yeah, if there's a loop, you can't. And then if you can, you need to keep track of the order in which you traverse it, and you return it as a list. Okay, first thought immediately is probably just pick a starting node and then try and go through. You don't really have a indication of what the first course you should take is. Let's see. Okay, I don't want to make the graph directly. Can I just, does it work if I just pick a random course? Let's see. If I pick a random course, you have a prereqs now. The prereqs I think are going to be the main thing you need to look through. So if there's a way we could just, I guess we could represent it in an adjacency list again. I'm just going to put that as a side note. Okay. We pick a random course, I guess. We go through, we check if there's prereqs? Pick a course, check if prereqs. If there's a prereq, that means you have to put the prereqs before. But now you have a bunch of prereqs that you need to check. So I guess you could do this working backwards kind of an idea. You check if each prereq is possible. Take a random course, check prereqs, and then for each prereq, you then continuously grab their prereqs if you've already encountered it. So yeah, if for each prereq you recurse, and then you need to check that if you've already encountered this course before, that means the course is actually in the future. Or you're at a prerequisite, and the course, which means the course you have already seen, requires your current node as a prerequisite. So if you see that course again in when you're looking for prereqs, that means you have a cycle. So for each prereq, if you've already encountered, that means there's a cycle. And then when we have if it's impossible, do we just return an empty list? Would that be fine?
That's fine, yeah, that's fine.
Okay. Yeah, so there's a cycle, if cycle, return empty list. Empty list, okay. I think that works, just broadly. You take a random course, you just do like a backwards traversal, or like a DFS, I guess, for each prereq. Yeah, because you don't want to do a BFS, because that just like mixes prereqs together, and that doesn't make sense. Check the prereq. For each prereq, you need to check if it's already possible. So what's the end state here of your recursion? If there's no prereqs, that means your course is free to take. Yeah, so your end state is if there's no prereqs. Okay, that seems feasible. I'm going to make a DFS function for now then. I don't know if I need it. I'm gonna layer on this logic to make it more like clear and structured, I guess. So okay, so given a course, check prereqs. If prereq is already encountered, so we need to like track encountered somehow. Track encountered courses. Cool. If prereq is already encountered, cycle, return empty list. If prereq is not encountered, start recursing. Recurse, as in like go back to the start of the function, you are now given a new course and check the prereqs. And the final thing would be like, yeah, loop through every course and then see if there's a prereq chain. Loop through every course, check if prereq chain. Cool. Track encountered course. This encountered course thing has to be specific for each loop, which means I guess I'm putting it down here. Needs to be local for each loop. Cool. Okay, so I will need a recursion. I guess this will be called check prereqs as my DFS. I'll need to put it above the function so it actually gets defined. Actually, I'll just define it in the function. Who cares? Okay. Check prereq, you're given a course prereqs, and this prereqs is specifically only the ones for the course. Ooh. And now the problem is, how do you get this list of prereqs? I probably need a dictionary, which means, okay, for each course we also need to make a dictionary. Predict from course to all prereqs, and I guess this would be a list. Okay. Loop through every course, check if there's a prereq chain. So yeah, now you can get the prereqs for the course. And now you can loop through it. So you have a course, you have the prereqs of that course. They're going to be of the structure. So your course is an index, which means this would just be 0, and then your prereqs would be. This is inefficient. I don't need course, and okay. Prereqs should be a list of just the prereqs, not the tuples. So to take course 0, you need to take course 1, which means your prereq in this case would just be a list of 1. And then if you had an extra prereq, I guess you could call it 2. Okay, so this would be if your prereqs were like 0, 1, 0, 2. Okay, cool. Okay, so I need to define this DFS now. Now that we have the course and the prereqs, we just go for prereq in prereqs. Oh, I also need the local stack. Let's call it traversal. Visited courses, that's fine. All right, for prereq and prereqs, for each prereq, if it's already visited, not good, you have a loop. Okay. If prereq in visited courses, return, okay, we need to return something. I'll just return none for now. I don't know what I'm returning in this function. if prereq in visited courses, return something. Otherwise, you need to recurse on it. Else, return check prereqs. And now course doesn't matter. I don't think I'm using it. So let's see. We need to do. I think I'm doing this in the wrong order because now I need the dictionary, which is here. Okay. Prereq map at prereq. Okay, so you get all the prereqs for the course, and then you just pass in visited courses. Okay, and I guess I'll put in course for now. It's not the only two cases. If the prereq is in a visited courses, you return none. Otherwise, you return the result of your DFS. I guess so. Yeah.
What if it doesn't enter the loop? Is that possible?
What if it... sorry, do you mind repeating that?
Yeah, like what if it doesn't enter the for loop? Is that possible?
Doesn't enter the for prereq and prereqs. Well, if it doesn't, that means that there's no prereqs, which means, yes, it is possible. Sorry. Okay, now I need to figure out what exactly I'm returning. I'm gonna, return true, okay. The problem here is, like, we could return true or false, but that only tells us if it's possible. We want an ordering. And now, the question is, what is representing the ordering? I guess it is visited courses, but that's not... I was planning on visited courses on just being a set. So,
well, hold on. So, I want to ask about that really quickly. What do you mean by ordering? So, what is the goal of check prereqs?
The goal of check prereqs is to check if good question. Check prereqs, I guess the initial goal was check if there's any loops. That was the main reason I was recursing. It's check prereqs is supposed to be the thing that's like recursing backwards.
Okay.
If that makes sense. So
yeah.
Ideally, yeah, we traverse all of the prereqs to create like a chain, and then you would store the ordering in some sort of like backwards order, because you start with a course and then you can like point to all of the prereqs.
Yeah, okay.
And find order just requires a list of any order. So okay, so if we want check prereqs to return the ordering, hold on, I think I've confused myself. I'm going to go back to check prereqs because I think I need to figure out what this like loop through every course is doing. And if I figure out that, I can actually figure out what check prereqs is going to return. So we loop through every course, check if there's a prereq chain. If there's a prereq chain, we call check prereqs on it, and it returns something. And then we have to figure out, check prereqs will maybe return us, has to tell us if there's a prereq chain. So if there's like a loop, we need a node to return this. Otherwise, we now need to create some sort of order with the output that we've been given. That's the problem. That's a problem. If check prereqs returns a list of courses, if check prereq returns a list of courses, then you have a chain right there. But the problem is it has multiple chains of things that it goes through. So if we have like 0, let's say the order is like you have to take 1, 2, then 0. But you can also need to take 3 and 4, and then 0. So you loop through every course. Let's just say you start on 0, and then you have the prereq of 2, and then you have the prereq of 1. but you also have a prereq of 4 and a prereq of 3, which means you're basically calling 0, and you call check prereqs of 2, and then you call check prereqs of 4. And then you call, no, it's DFS, which means check prereqs of 1 and check prereqs of 3. 3. Okay, if it returns a list, well, it can't return a list. So check prereqs of 0 would then have to return like a 2D list or something like that. And then you'd have to restructure that. Okay.
So you're trying to get the check prereqs to just basically find the ordering as well, or find possible orderings for the input, in this case being
I
0?
guess so, yeah.
Okay.
Yeah, I'd want to make it return this, because then from that output I can just form the list that I want.
Okay. My first question is, how do you know to call it with 0?
I guess this is the worst case.
Right, but let's say you wouldn't know that 0 is at the end.
Yes,
Unless you
you're right.
pre-process it, which you could do obviously, but you haven't. So let's just so you could just call it with 2, which would give you 1 to 2, because that's the only valid ordering for 1 to 2. You get 1 to 2, and then so what?
Yeah, and then the problem is then you'd call it with 0, and then you'd have, like, if the for loop goes through every course indiscriminately, that means there's a good chance it'll go through a prerequisite and then go through the root node, which now we have like duplicates.
I mean, it's guaranteed to go through the 2 you said, not a good chance. Okay. I think this is something you said earlier about how, it's still right here, is that if there's a loop, it's not possible.
Yeah.
Right? Does this also mean that if there's no loop, it is possible? Have you thought about that?
If there's no loop, yeah, it should be possible.
Okay, cool. So
you have a chain.
Right, so we can kind of, and so we can just deconstruct this problem a little bit, right? So let's think about it in terms of a cycle detection. If we find a cycle, it's not possible, return empty, right? So,
yes.
And for the sake of time, we won't implement that. That's whatever. Now let's guarantee that there's no cycle. Let's say there's no cycle. We guarantee that we checked it. Blah blah blah, right? If there's no cycle, what can you do? Like,
there's no.
What you said here could also work, right? But like you said, let's say we call it on 2, right? So it's already commented out. So we call it on 2, and I'll just call the function f because I don't want to type it out, right? And 2 will tell you, okay, so on 0. This will tell you it must be 1. Actually, you know what? I'll say 2. So it's 2. Then we know it must be 1 to 2, right? Like, this is the only valid way in this detail,
yes.
right? And then we can call it f of, let's say, 4. Then we know this must be 3 to 4, right?
Yep.
Right, 3 to 4, 1 to 2, right? We can know this, right? And then now let's say now we call f of 0. Now we know it can be 2 to 0, or 4 to 0, right? But it doesn't really matter. Yeah, it doesn't really matter, because if you go, okay, let's say it's 2 to 0. Now before we DFS on 2, let's check if we have an answer for 2 already, which we do, because we've done it before.
Yes. Okay.
So we can store intermediate paths, right? And if we know this is either 2 or 4, in this case, the way the problem is structured, it doesn't matter which one you pick, because they're both valid, because you can get to 0, right? So in this case, it's valid because you know that 2 is valid, right?
Yes. I see. Okay. Yeah. So we should not have recursed on check prereqs. Should have just been check prereqs, and then you just return. Wait, no, I have the prereq map already. So
you have the prereq map, exactly. Yes.
Yeah. So F2 is basically just look at the map, and it returns the prereqs.
Yep.
Wait, but what if, okay, F0 returns 2 or 4? Yeah, so it would just return 2 or 4 in that case. And then, okay, what happens after you look at the map? How do you go from f of 0, you go 2, 0, or 4, 0, and then you'd want to, and then you want to create the ordering from that.
Yeah. So in this case, you have 2 here, So let's say, with a loss of generality, we can just pick 2-0.
2-0, sure.
Right, and then so we know that 2-0. Well, and 2, there might be many ways to this. So for example, this might be 1-2, or this might be like 8-2, right? I mean, this could be many things. But again, we're only trying to return any ordering. So with a loss of generality, we just pick the first one we see. And so that means at this point, we know that everything we have stored as paths, like this is a path segment 1-2, this is path segment 3-4. We know that if it has a path, it is a valid one. So we can essentially collapse 2 into like 1, 2, right? So it's 1, 2, and then 0. So you know that this is a valid path because the subsequent prerequisites were also valid paths because we just picked an arbitrarily valid one, right?
I see. Okay. So you create like a general list for storing. You call whatever. Let's call F2. You just store it in the map. 1, 2, and then once you call f of 0. Wait, I still don't get when you would start storing things then.
So so that when you start storing, it depends on how you implement it. So I'm being a bit vague here, right?
Okay.
So it depends. There's a lot of ways that we can talk about that more in the after show, but that sort of depends. Now, what I will say is that it doesn't really matter. Like the truth is, it doesn't really matter how or when you store it, as long as you do store a valid path. And if you think about it, all paths are valid because there's no cycles. And so there's a bit more of a nuance that we can talk about later, but all paths are valid. You're just trying to return any given path. The key is to make sure you're not missing a path. That's the part we haven't really discussed yet, right? So to make sure we're not missing a path. Because for example, this could have been, right, like I could have said, for example, 1-2 or 8-2, or 8, that's not going to be valid, or 8-2, but 8 could have been a value too, or 8 could be a thing too, right? So it might be like let's say like 4-8 or whatever. So if you just return 1-2 in substitution, that's not necessarily just valid because you're not taking these courses. So you still need to take these courses. So for example, you could say 1-2, or you can say 4-8, and then you can put 1 anywhere before this 2, right? So you can have any arbitrary step before, and you can have 1 in front of that, right? Because I mean, one thing that we simplified is that we we have put the prerequisites right before the course, but they can be anywhere before, right? They could be infinitely far before.
Okay.
Right. So
I see. So you would if 4 had prerequisites, you just expand it infinitely.
Yeah, I mean, you can put it right before here, right? P4, or you can put it over here, right? As long as it doesn't have other prereqs as well. So you can put it anywhere before.
Okay.
But so that's a little thing for thought there. Do you have any intuition about the time and space of what you have written?
What I have written?
Yeah, what you have written.
Okay, let's assume that it's based on density. So check prereqs. My initial plan was I was going to loop through every course. There's going to be n nodes in, let's say there's n courses, which means you have a loop of n times. And then check prereqs would recurse, worst case, n times. Let's just say you had an entire prereq chain. And that would be the worst case, right? Is you would go to O of n squared.
Yeah.
Because you check every prereq and then you'd have to go all the way back every single time.
Okay.
And then space complexity, you have a prereq map. So worst case, it just depends on how many connections you have, I think, which means that it should be O of n squared as well.
Okay. Okay. That's fine. That's fine. It's a bit wishy-washy, but we'll get to that.
Yeah.
Okay. So let's wrap the interview here. I want to talk about some of the feedback. So, first of all, always asking, how do you feel about your performance today?
Okay, first one, let's see. I think, I stand by my choice of picking the adjacency matrix because I was more comfortable with that. The problem is I probably shouldn't have been more comfortable with that. I guess my skills with adjacency lists are much worse than with matrices. So I should probably not have that as I should probably be more familiar with adjacency lists. I think the algorithm was fine. Like the speed I did it was fine. Um, I avoided nested if statements just because I didn't want to write them. But at the end of the day, it seems like they were probably the easier choice to write. I think the function is correct.
Okay.
I think time and space was correct.
Okay. All right. Okay, we'll talk about that. Second one. I mean, obviously we didn't finish it, but
Yeah.
how do you feel?
Um,
How close do you think you got?
Not that close.
Okay.
Because I think the main thing I'm still hung up by is how do you like create the path specifically.
Do you know the keyword for the second problem, or was this like a fresh problem for you?
I don't.
Okay.
I know.
We'll talk about
I
that.
knew of the normal one, but
Okay. That is okay. All right. All right. So let's talk about that. I won't torture you with that one. First one. Let's start with the first one. So the first one, I think, a couple of things I wrote here. Great notes. Great pseudocode. That's just off the bat. That's a really good confidence for the interviewer to say, oh, this person knows what they're talking about. They have also built in. This is a key one I think that's really rare. I see these days because I am an interviewer, so I see these things. This one I don't see, which is that people also communicate how confident they are in a certain idea. I think that's underrated. So keep that up.
thank you.
What I will say is, this problem is, I mean, this is a Leetcode problem. You can just go find it after. I'll send you the notes. This is not meant to be a hard problem, and I think you wasted a lot of time on the easy parts of the medium difficulty problem. Okay.
Yes.
What do we mean by that? So there were some things like, for example, it just took you a little minute to set up the loop. It took you, I'd say, way too long to figure out the if statements.
Yes.
At your level, by the way, you were a bit, generous with yourself with the level there. I think you could definitely do things that are a bit harder, but this should not be taking you any time. Okay.
Yes.
So this problem in total from start to finish should be 50 minutes max, and you should aim to do it in 10 minutes on your own practice. Okay.
Okay.
Why do I say that? Because this problem actually doesn't have any skill. The only skill is when you think of the algorithm, right? The algorithm, coming up with the algorithm is a hard part. But you quickly realized you can just always assume, in these cases, right? So you figure that out pretty quickly. And then actually executing and writing out the code for this stuff, there's not very much difficulty there, so you shouldn't be taking time on that. Okay. So I think there's a bit of practice that's needed for just execution of ideas. Your idea was good. You came to it very quickly. Good diagram that you drew. Okay. But the execution here was a bit weak, and you could have been faster.
Yes.
And you should have been faster.
Sorry, to go more in depth about
Okay.
that. Which parts of the execution specifically do you think?
So that's a good question. What you've written here today, the part that I would say could have been faster is the moment you come up with the 3 cases per, you should immediately be like, okay, this is a 3x3 grid of scenarios. That's 9 cases. I need 9 return statements, or I need 9 whatevers, right? So that's if, else, if, elif, else, and each one has that too. So that's 9. So it's like, okay, I need 9 cases. These are 9 cases. Boom, 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 right? One thing I did know is a bit of a nit here, which is that you knew there were 9 cases the moment you wrote these 2 down. I mean, or you should have been able to know, right? So
Yes.
you should just say, I got 9 cases. I need, just route the rip, because you were a bit hemming and hawing. This case need to be a surprise to you, not a surprise, but this one is and then this must mean that it's a beginning. So that shouldn't be a surprise. That shouldn't be news. 9 cases should be coming out ASAP. Okay, so that's a bit of practice. So that's the first thing I'll say. And then one more thing I'll say that's a bit more high level is. This problem, by the way, you solved it correct. This is a good solution. I don't think there's any issue with that. What I will say though is that this is one of many ways to do the problem, and the more typical way to do it. And the reason I'm mentioning this is not to say that your solution is bad, but to give you a strategy, is that you should be thinking of algorithms to solve a problem that you are familiar with. So what you've written here is definitely a solution. Nothing wrong with that. However, there are also other solutions that you might be more comfortable writing. So for example, you can do this with DFS or BFS, right?
I
So
see.
for
I cannot see that.
right, so then that's valid. So you did what you could, right? But you should always be thinking about it. Oh, I'm gonna do this novel algorithm I don't really know. Maybe I'll take a second to think if there's a more familiar one I could use, right? So you can go Leetcode, you can find the solutions. They're going to be mostly in BFS and DFS because again, it's a strategy. The strategy is to reduce any problem to one that you're familiar with. And that helps with many things, like for example, edge case checking, solution checking, but it also helps with execution time. Okay, like as in like writing time, like typing time, right? So just be aware of that. That's a strategy thing. I think you're good enough now that I can start talking about the strategies. So be aware of that. Take the extra 30 seconds, 1 minute, just to think about if you can reduce the problem. Okay.
Yeah. I'll look into the BFS version.
Yeah, you can go find it after. It's very obvious as well. All right. Okay. So one more thing I want to say about this one is time and space complexity. In general, these problems you actually want to, for graph ones, you want to have a variable for the number of nodes and a variable for the number of edges.
I see. Okay.
Usually, once you get to the level where you're talking about graph problems, you don't want to just bound all problems as n squared, because then every graph problem is basically n squared, right? So instead, what you would rather do is you would say, hey, this is, let's say, v plus v. By the way, usually people use v plus e, right? Vertices, edges. Vertices is usually n, right? Edges might not be n squared, right? But if, for example, this one you say, hey, this is actually v plus e squared, sorry, v plus e, where e is proportional to v squared, that's a much better answer, because even though, yeah, that's technically still O of n squared, it's a much more precise answer, and that gives interviewers more confidence that you know what you're talking about, right? So just be aware of that. Last thing I will say, one thing that is a bit more high level about this problem, and why I said this is not the solution, this is not the question itself, by the way, but why I said you can pick an input is because I want to see how quickly you can recognize that the optimal input for this problem is actually an edge list. So if you can pick an input for graphs, most people won't let you do that, but you should always be thinking about it.
Yes.
An edge list will be optimal because that gives you optimal iteration order. However, while most people won't let you pick your input, why you should still think about it is you should think about if you can reduce your input to the optimal input for no time penalty, and that might be able to save you time. Like this is in the what I call in the realm of pre-processing, right? So pre-processing graphs in this context means switching the different input types between each other to see if you can get yourself an edge. Okay.
Okay.
So that's a strategy as well in this case, just to think about. All right. Any questions about the first problem?
Nope. That sounds good to me.
All right, second one. Now this is obviously, this is a miss here. This is a more difficult problem, but it's not that much more difficult. So let me just say two things real quick. The first thing, and the reason you couldn't solve this, and the reason that most people don't solve this, is not because the problem is too hard. You can actually solve this problem. The reason you can't solve it is because you don't know about the topological sorting algorithm that is needed for optimal solutions.
I see.
So I'm not going to say that here. Obviously, just go study that yourself. Okay. What I will say is that you don't need. Now, people really get caught up on that. Oh, this is a topo sort. I gotta do it. No, look, that's the optimal way to do it. But if you don't know it, you should still be able to solve it with another potentially suboptimal algorithm. So this is a thing where you had a good idea. You write down your notes, you write down your ideas, but you didn't buy in to your own algorithm. So one reason, there's a couple things I'll say here. The strategy again. First of all, great idea with the DFS. You can definitely do a DFS, right? But one thing you got to be very clear is what is this thing going to return, right? DFS. What's a DFS going to return? Is a DFS going to return a path, a boolean, a thing, a whatever, right? So there's a lot of different ideas there. So when you're writing these helpers or other functions or assumptions, you want to make sure your types or return values are very, very clear, right? So that's the first thing I'll say about that, first strategy. Okay. Now the second thing is, this is not, maybe not strategy, but this is a more like a pattern recognition. Okay, what I mean is when you're thinking about things like, for example, this course scheduling problem, and I've asked you to actually return a valid schedule if it exists, or ordering if it exists, right? You should recognize, oh, this is actually a more difficult version of the problem where you only return true or false, right? And I believe that's actually a question you asked early on, was like, what's the return, right? Like, is it going to be Boolean or the path? Right. So even though this is a more difficult variant, you should still, if you can't find something immediately, think about the more basic one, right? Think about, okay, well, what if it was only true or false? What would be my solution? Okay, I can do it that way. That might be easier for you to figure out. And then say, okay, well, let's say I have that. Now I'm asked to return the path, right? Now I have to return a path. What do I need to change? Right. So that's like two incremental problems instead of like one bigger one. And that, I think, can help you. Now, why do I think that could have helped you in this case was because you did recognize that if there is a cycle, it is not possible. And you also recognize that if there is no cycle, it must be possible, right? Yes. So essentially, the quote-unquote simpler solution, which is just return true if it is possible. That's basically just a cycle detection problem. So this problem should have been broken down, if you don't know topo sort right off the rip, is it should be broken down into cycle detection and then basic BFS or DFS. So that's kind of a bit of a overview of how you could have approached this problem if you didn't know topo sort. Okay.
Like it should have been 2 parts. One, first look at a cycle, and then 2
Yes.
do a. Okay.
Yeah, topo sort lets you do both at the same time.
Okay.
Yeah, topo lets you do both at the same time. But if you don't know it, you don't know it. You can't do anything about that, right? So keep it simple. Keep it simple. Do the cycle part first, and then say, okay, after this line over here, I can guarantee there are no cycles. Now I will just do a DFS or whatever to find an ordering, right? Because or BFS, anything works, right? If there's no cycles, then all of them work. They can give you any ordering, slap all the non-connected components to the front, and then boom, right? So
yeah,
like that's just a strategy thing. Like reduce the problems into the easier ones, even if that's not what you're trying to do here. And that's often that won't work 100% of the time, but that will more often than not be worth the time to think about it. Okay.
Okay.
So just be aware of those some strategies for you. And by the way, I'll just say for this problem, especially when I ask candidates, it doesn't matter if they don't get topo sort. That's not the key, because again, testing topo sort is a pretty worthless skill. I really don't care if you know topo sort or not, right? But if you don't know it, you better have a strategy. Like you should still be able to figure out what the strategies are, right? So just be aware that it's not like you failed because you don't know topo sort. No, you still could have done a lot more to kind of patch it up.
Yes.
All right. Any questions or about these problems, or just in general about the interview?
Okay. I think, was it a good idea to even guess a time complexity for the thing for my second question? Because
usually, that was for my purposes of giving you feedback.
Okay.
A real interviewer would not ask you that because there's no signal. Like basically, the interviewer trying to try signal. They're trying to figure out, is this person good or not? And if you didn't even come up with the algorithm, there's nothing to be talking about for efficiency. The reason I asked is because I want to see if it was a coincidence that you didn't use V plus E, or that you just don't like using V plus E. Right. Okay. And I want to understand, okay, well, what level are you? Where are you with the graph understanding, etc. So that's for me to just give more tailored feedback and not for actual evaluation. Yeah.
Okay. I see. Yeah. So I think in general, I need to know more graph algorithms and then just do more graph problems to get like V plus E, time complexity, and then develop some strategies for it.
Doing graph problems is an easy way to kind of get good at that, but it might not be efficient in terms, like if you're bad at graph problems, you probably should work your way up, right? But these are the reason why I like asking graph problems for more confident or competent and confident candidates, is because there's a lot more strategies and solutions to solve any problem. While for a lot of other algorithms or problems, there's only really one optimal way, and that's kind of like, do you get it or not, right? But for graphs, there's a lot more strategy behind it, and that gives you a lot more information and signal. So.
Okay. Is it possible to practice like strategy finding in other questions? Because typically, it's
absolutely.
Like, I see some keywords, and then I guess like, oh, it's this algorithm.
The way I would can practice, I mean, there's a couple ways to practice it. The most effective way is to get people to ask you questions that they know intimately and that they can point out where you could have done certain things. That's not very economical, because that takes up a lot of people's time, and it takes up a knowledgeable person's time, so that might not be feasible. What I would recommend is, when you go on Leetcode, find a more difficult problem. Like start from the hearts, and then what you should do is you should just try to do it. You should crash and burn, and then say, all right, great. Now what you're gonna do is see the related problem, similar problems tab, and then find ones that are medium in the solution in the similar problems, and then go do the mediums, right? And then say, oh, was this similar because of that? Was it similar because of that? Right. So what you should be teaching yourself is, you're at a hard, you can't do it, or if you can, that's even better, right? But you probably can't do it, and you can't do it, but you can do the related medium problem. And so in your mind, you should be thinking, okay, how does this medium go to that hard? If I'm faced with that hard again, how can I think of this medium? So that's how I would practice it, especially for graph problems.
I see. Okay, that makes sense.
All right. Anything else?
I guess I think that's mostly it for me then.
All right. Well, thank you very much for the call. Talk to you later. Take care.
All right. Thank you. Take care.